Okay, one of the things we talk about in algorithms all the time is the concept of a canonical problem. And so you can think of a canonical problem as sort of a benchmark that we use to try to understand how to optimize algorithms, how to design algorithms, how to make them work better. And so one of the core and very simple canonical problems that we have is the sorting problem. Right? So sorting is something that it's likely you'll never actually sit down and write a sorting algorithm, and yet we can gain a huge amount of insight into various kinds of sorting algorithms and other kinds of algorithms as well by understanding the approaches to sorting. Right? So one of our key canonical problems in this class is going to be sorting. It's very, very likely that you've run into sorting algorithms before, right? And so the problem with sorting is given an array of orderable things, right? Things that you can, if I take two of them, you can tell which one is bigger than the other, right? That's basically what orderable means. So given an array of orderable things or objects, or typically this will be numbers or characters. Return the array sorted from smallest to largest. Right? Return the array in order. And in this class, our core assumption is going to be that in order means from smallest to largest. Right? So non-decreasing. Okay. And there's a variety of sorting algorithms that you've likely seen, right? So some of the algorithms that we run into for this are things like selection sort, right? So selection sort is the one where you begin at the front and you walk down the array, find the smallest thing, right? So you keep track of the smallest thing you've seen, and then you swap that thing for your location, right? For the location where you started. So you go find the thing that belongs where you are, put it there, and then step forward. So what selection sort does is it builds up a sorted array from the front, essentially. So selection sort, two for loops, build sorted array. Whoops. From the front. Okay, and selection sort is one of the kind of the classic brute force sorting arrays, sorting algorithms. And when I say brute force sorting algorithm, I'm typically going to mean it's a quadratic time algorithm, and it's quadratic time, and you can essentially see this because it has these two for loops, right? The two for loops come from the fact that I have to say where I'm here. And then my second, and I have to be somewhere, be at each of the array indices throughout the progression of the algorithm. And then when I'm here, I have to walk down the array in front of me to find the thing that belongs where I am. Okay, so selection sort is an n-squared algorithm. Another one that you'll run into is bubble sort. And so if you aren't familiar with these algorithms, I am expecting you to go find them, right? Go find them and at least gain a cursory understanding of how these algorithms work. So I'm giving you a cursory understanding here. Go find some pseudocode, practice doing the analysis, make sure that you understand what's going on here. So bubble sort is another one that you could think of as kind of a brute force algorithm. And so the way bubble sort works is you stand in a place in the algorithm in the array, and then you look at the next element. If those two are out of order, you swap them, and then you walk forward. And you do that again and again and again. And so each of your outer loops, you essentially comb through the algorithm, find the largest thing, and push it all the way to the end. And so it's called bubble sort because there's this sort of analogy of, you find the largest thing and then you make it bubble up through the array or something like this. So bubble sort is another one that's brute force. It's not efficient. It also requires many swaps, and it's not a particularly good algorithm, but it's one of these sort of basic knowledge things, right? That you're kind of expected to have. In the undergrad version of this class, I teach both selection sort and bubble sort. In the graduate version, I'm expecting you to go and find out, the definitions of these yourself. We aren't going to use them, but we are going to compare other algorithms to these, right? So these are they're sort of the basic, less interesting benchmarks that we're going to try to improve upon as we go forward. Another one that also shows up in the book is insertion sort. I'm not going to talk much about that here, partially because it's also an n-squared algorithm, right? And then there's all these other more kind of more sophisticated, more interesting sorting algorithms that we'll run into in the course. So we'll talk about merge sort. Merge sort is faster than n-squared. We'll talk about quick sort. Quick sort, it has a worst case n-squared running time, but by being clever with how we run the algorithm, we can actually make it faster than n-squared in most cases. We'll talk about something called counting sort. And counting sort is a special sorting algorithm that requires a little bit of structure on its inputs. But by using the structure on its inputs and in a clever way, counting sort can be a very fast algorithm, much faster than the other ones we see here. And that's going to be our kind of, this list here will be our approach to sorting algorithms. So everything above this line, you are responsible for this stuff. And I will teach you this stuff, right? So I teach at some point in this course, right? So I bring up sorting because this is something that we'll come back to again and again. So it's worth being familiar with. In fact, in just a week or two, as soon as we start talking about divide and conquer, merge sort is going to be kind of our first really interesting canonical divide and conquer algorithm.